Check it.
Okay, welcome back. Today we're going to be talking about radicals and imaginary numbers. We'll start off with radicals. Now, what's a radical? A radical is this symbol right here, which you might refer to as the square root symbol. But the fact is, it's more than a square root symbol because you can also use it for cube roots, fourth roots, fifth roots, and this will go on forever. Any nth root, really. So 17th roots, whatever. So I'm going to refer to them as radicals, not always just square roots. Now, how do you simplify a square root? Well, if the number you're square rooting is a perfect square, meaning it's something squared, then it's easy, right? Well, we already know that the square root of 64 is going to be 8. We know the answer here. But why is it the answer? It's because 64 is equal to 8 squared. So the square root of 64 is the square root of 8 squared. And the square root and the square are opposite, so they'll knock each other off here, and you'll get an 8. So the idea is, can you figure out what perfect squares are in 64? Okay? Now, 64 is easy because we all know our times tables. We know that 8 times 8 is 64. However, what if we didn't know that? We could do the following. We could take 64 and factor it down all the way down to prime numbers. Okay, a prime number is a number that has no factors, meaning no numbers go into it evenly, except for 1, which goes into everything, so that doesn't count. So let's factor 64 down to primes. Now, you could do this a bunch of different ways. I'm going to do 3 ways here. You could go 8 times 8, obviously. You can go 16 times 4, or you can go 32 times 2. All of these are factors, right? But none of these are prime numbers except for this 2 over here. So what you have to do with a factor tree is keep going until you get to prime numbers. So this becomes, let's say, 4 times 2, this 8 here, and this 8 also becomes 4 times 2, right? And this 4 here still becomes 2 times 2. Now this is already prime, so this will just stay the same. This 4 becomes 2 times 2, and this is prime, stays the same. And you can see why it's called a tree. It has a triangular shape. Now you can see, do we have, and this is 2 times 2 times 2 times 2 times 2. So this is 2 to the 6th power, okay? 2 times itself 6 times. Now, do we have any perfect squares here? Well, actually we do, because look, this is 2 squared, right? That's 2 squared. There's a perfect square right there. Here's another perfect square right here, 2 squared, right? And here's another perfect square right here, 2 squared. So we can, okay, rewrite 64 as 2 squared times 2 squared times 2 squared. Well, that means the square root of 64 is the square root of this times this times this. Okay? And that's going to be, well, square root knocks off the square in each one of these. Once again, no absolute value to worry about here. So 2 times 2 times 2, which is 8. Now, it doesn't matter how you make your factor tree, you will end up with the same roots. Like, for instance, if I start off with 32 times 2, 32 times 2 becomes 8 times 4 times 2, and this becomes 4 times 2, and this becomes 2 times 2, and this becomes 2, and this becomes 2 times 2. This is 2, this is already 2, this is already 2, this is already 2. Look, same thing. You still have your 2 to the 6th power. It's exactly the same at the end. Doesn't matter how you got there. Okay, but the important thing is, can you spot all the perfect squares? Now, naturally, this is not necessary if you have a perfect square. And I made a list of perfect squares above each question here so that we can take a quick look and see if there's a, this is 1 squared, 2 squared, 3 squared, 4 squared, 5, 6, all the way up to 15 squared. And 64 is on that list. It's right there. It's a perfect square. So we don't have to do very much work here. There's a shortcut. We can just jump to the answer. But what if it's not a perfect square? Like 98 here. 98 is not a perfect square. It's not on this list. Okay, it's somewhere between 81 and 100. So it's somewhere between 9 squared and 10 squared. So it's going to be, if you did it in decimal, which we're not allowed to do here, you would get 9 point something. Okay, if you tried to do this with a calculator, but we don't want the decimal. We want to reduce this, simplify this with no decimals, get an exact answer. So what do? Well, I'm going to make a factor tree and break it down. So 98 can be broken down into, and this is where you might reach for a calculator and, like try some numbers, like plug some numbers into a calculator. So I'll just do that real quick, just to show you how that might work if you didn't know what you wanted. So 98, and just divide it by, I don't know, 5, and you get a decimal. So 5 does not go into 98. Well, how about 6? 98 divided by 6, so on and so forth. Nope, decimal doesn't work. 6 doesn't work. 98 divided by 3, that sort of thing. All right, so you might want to try something like that. How about 98 divided by 7. Hey, 14, that's a whole number. That means 7 times 14 equals 98. So if I want to use that combination of numbers, let's do that. So 14 times 7. Well, 14 can be broken down. It's not a prime number, so it can become what? 2 times 7, right? So 2 times 7. And 7 is a prime number. You can't break down 7. It's just 1 times 7 and that's it. So just bring it down. And there you go. There's your prime factorization. Do we have any perfect squares in here? Yeah, we do. We have 7 times 7. That's 7 squared. So when you go, what does that mean? It means that 98 equals 7 squared times 2. You got 7 squared and you got 2. So the square root of 98 is the square root of 7 squared times the square root of 2. Now take the square root of the perfect square, you get 7. Now can you do anything with this? 2 is a prime number. You cannot break it down. If you try to square root it with a calculator, you'll get a decimal. We don't want that. So basically leave it alone. If you cannot break it down, it's as simplified as it can be. So the square root of 98, or radical 98, is 7 radical 2. That's how you pronounce this. You could say 7 square root of 2, but it's a lot of syllables. So we say 7 radical 2. And that's how you would pronounce this. So here we have 243. We want to square root 243. 243 is not, well, actually, if I made this list a little longer, this is 15 squared, which is 225. 16 squared would be 256, okay? And 243 is in between that. So you know it's somewhere between 15 and 16. So it'd be like 15 point something, but we don't want a decimal, so we're not going to use that, right? So 243, how can you break it down? Once again, you can take some guesses, right? Or you can grab a calculator. We'll grab a calculator here and just try out a couple numbers, okay? 243 divide by, I don't know, 6. Nope, no good. 243 divided by 7. Nope. 243 divided by 8. Nope. 243 divided by 9. Hey, 27. 9 times 27 apparently equals 243. So that's one way to go. Okay. So 9 times 27. Neither of these are prime numbers, so we have to keep breaking them down. This is what? 3 times 3. Those are prime, so those are done. And what's 27? Well, 27 is 9 times 3, isn't it? We need to break down this 9 further, so all of these come down, the prime numbers, this 3, and this 3 all come down, but this 9 becomes 3 times 3. And what we see is that 243 is actually 3 times 3 times 3 times 3 times 3. It's 3 to the 5th power, no matter how you break it down, okay? And are there any perfect squares in here? Yeah, here's a 3 squared right there. Here's another 3 squared right there. And here's a 3. So when you want to square root 243, you can square root 3 squared times another 3 squared times a 3. This stuff down here. And this becomes, well, square root of 3 squared is just 3. Also 3. So it's just 3 times 3. And this right here is not going to simplify, so that just remains a radical 3. So we get 9 radical 3, and there we are. Okay, this next section is about imaginary numbers, or specifically imaginary roots. Okay, we spent the last few lessons learning how to solve quadratic equations using either factoring, completing the square, or quadratic formula. And one of the main reasons why we solve quadratic equations is to find the x-intercepts of a parabola. They're really important, and we need to be able to find them. So how do we find the x-intercepts of a parabola? We would make the y 0, and we would solve this equation, okay, by factoring usually, okay? Or if we couldn't factor it, we could use either completing the square, or we would use the quadratic formula. Okay, usually it's factoring or quadratic formula. Those are the two main things. And when you were learning how to solve an equation with the quadratic formula, because this is not factorable, this particular one is not factorable. You could try to reverse FOIL it, it's not going to work. So if it's not factorable, you have to use quadratic formula. And when you use the quadratic formula, you would check the discriminant, the b squared minus 4ac. And the b squared minus 4ac, there's b squared minus 4ac. You would get 16 minus 20, so you get a negative 4, and that tells you have no real roots. So if you were to graph this parabola, it would have no x-intercepts because it has no real roots. What I did mention, however, is when you had no real roots, you would have 2 imaginary roots, and I'm going to show you that visually now. So let's go over to Desmos here. We have the exact same parabola, y equals x squared minus 4x minus 5, sitting right here. And you can see clearly it does not touch the x-axis. It does not have any x-intercepts. So where are these imaginary roots that we're talking about? I'll show you where they are in a moment, but let's just recap visually how this works. You could have, I'm going to change the parabola, I'm going to move it down. You could have a parabola, a different parabola, that is down here, for instance, right? Its vertex is below the x-axis, and because it's going up, this is a parabola that's going up, it's going to cross the x-axis on the way up, and it has true real roots. There they are. The other possibility was that if your discriminant was 0, you would only have one answer. Well, how does that look? That looks like this. When you have your vertex sitting right on the x-axis, that would be one real root. But as soon as you go above your x-axis, rather, as soon as you're up here, that means you're going up from a place that's already above the x-axis, so you're never going to cross the x-axis. This has no real roots, like we already established, okay? The discriminant told us that before we even looked at the graph. However, it's useful to know what the roots would have been if this parabola, this exact same parabola with this exact same width, with everything with the exact same vertex, if we just pretended that this parabola was facing in the opposite direction, what would the roots be? Okay, let's pretend, let's imagine that we could take this parabola and leave it hinged right here at this vertex and just swing it down like you would like a door knocker or like one of those things on your dresser, right? The handles on your dresser, just swing it down. And it would look like this. Okay, same parabola, same width, same vertex, but just pretend, imagine that you swung it down this way. Would the imaginary parabola have any x-intercepts? Would there be any imaginary roots? And yeah, there's one here, and there's one here. Now, these aren't real roots because they're not on the real parabola. They're imaginary roots because they're on the imaginary parabola. So yeah, you have these two roots, and the way it works is here's the axis of symmetry. See that 2 right there? That's your axis of symmetry. This real root, sorry, this imaginary root right here is a 3. So you think of it as 2 plus 1, and this is a 1, this is 2 minus 1. So from the center, this is 2 plus 1 imaginary unit and 2 minus 1 imaginary unit. So we're going to learn that that means later on 2 plus 1i and 2 minus 1i, and that would be the two imaginary roots. That's how we write them, but we're not going to get into that right now. Let's just go back to the chalkboard here and talk about how to find imaginary numbers. Okay, so we'll talk about imaginary numbers by starting with a question. Can you square root a negative number? Okay, like for instance, can you square root negative 25? And if you're not paying attention, you might think, well, the square root of negative 25 is negative 5 because the square root of 25 is positive 5, right? And the answer is no, it doesn't work like that. If you square 5, you get 25. So if you square root 25, you get back to 5. However, if you square negative 5 times negative 5 is also positive 25. So there's no way you could square a number and get a negative 25. It's not possible. You square negative 5, you get positive 25. This is not possible. So you cannot square root a negative number. The answer here is no. So this prevents us from doing the square roots of a lot of stuff. And with the quadratic formula where you have negative b plus or minus the square root of a discriminant, last time the discriminant was negative 4, right away to over 2a, right? That was your quadratic formula, and your discriminant was negative. You would have to stop and say, oh, no solution, because this is negative, because you can't square root a negative. Well, we're going to pretend, once again, like we can square root a negative. We're going to find the imaginary roots that make this thing work, okay? Called the orange dotted version of the answer, so to speak, from the Desmos demonstration. So how do we deal with a negative inside of a square root? That's going to bring us to imaginary numbers. Okay, let's try this again. How can we take the square root of negative 25, but in a way that is not going to violate the whole rule where you can't square root a negative? Well, we're going to use that method that we learned in the beginning of the lesson, where we're going to break down this 25. Forget about the negative for a moment. How can you break down 25? Well, you can break it down to 5 times 5, right? So the factors of negative 25 are 5 times 5 times negative 1. Okay, and that means if you square, and this is 5 squared times negative 1. Okay, and if you square root each one of these, that would be the square root of negative 25. Now, you can definitely square root 5 squared. That would just be 5. So that part of it is real. That's 5. But this thing right here is impossible. You can't square root a negative 1. So to make up for that, we're just going to have a definition here of something called I. I is the imaginary unit, I for imaginary. And what you saw on the Desmos demonstration, this is the distance between the axis of symmetry and the imaginary root. Okay, that's what this is. All right, it's one box on that graph. And the definition of I is that it is equal to the square root of negative 1. So this thing right here is what we call I. So this we can do, this we cannot do, but we have a name for it, we call it I. So what's the square root of negative 25? It is 5I. Because, to make a long story short here, you take the negative part out of the square root. Okay, so this is negative 25. You take the positive 25 and you take the negative part and you throw it out into its own radical. The square root of 25 is 5 and the square root of negative 1 is I. Now there are no plus or minuses here. There are no absolute values here because we're not dealing with variables. It's just, here's the important thing is this. You're not square rooting a negative here. You're square rooting a positive 25. And then the negative part that would be the troublemaker, you're giving it a name, you're calling it I. And that's the definition of I. Okay, let's try another one here. We have the square root of negative 150. How do you take the square root of negative 150? Well, for one thing, 150 is not a perfect square, right? It's not on this list of perfect squares here. So we're gonna have to break it down first. So first and foremost, let's break that down. So let's see, 150, we can break down to, let's say 25 times 6, right? And this becomes 5 times 5 times 6. This can still be broken down to 3 times 2, but these are both prime numbers. So we have 5 times 5 times 3 times 2. That's the full factorization. So we have here a perfect square. We have 5 squared here. But then we have times 3, which is not a perfect square, and times 2, which is not a perfect square. So 150, when we take the square root of negative 150 here, it's going to be 5 squared, which is 25, or 5 squared, either way you want to write it, times 3 times 2, but then you have this negative here, so times, all right, negative 1. And I hate to write the negative 1 like this because it looks like subtraction, so I'm just going to put it in parentheses here, negative 1. Okay? And now to square root this, you're going to have to square root this and this and this and this. Okay? And now the parentheses aren't quite as necessary because you have a radical there. So this becomes a 5 because the square root of 25 is 5, the principal root of 25. This radical 3 and this radical 2, you can't break them down, so they stay the way they are. And this is what we call I. Okay? However, the way I've written this is a complete mess and I have to fix this up. Well, if you have two radicals that cannot be simplified, you can just multiply them. So this becomes 5 radical 6. And then we still have that I there. So that's the first thing. We already tried to break it down. There's nothing in there that can be broken down, so you just multiply kind of those into one radical. The other thing is that you cannot put anything after a radical. Why? Well, I've made a conscious decision to keep this I really far away from here, but a lot of times what people will do is they'll write their radical and they'll write their I, and it looks like the I is inside the radical. So to avoid that ambiguity, to avoid that mistake, what we do is we always avoid putting anything after a radical. So what we'll do is we'll take this I and we'll stick it here in front of us. This becomes 5I and then radical 6. And that's how we write our final answer here. Square root of 150. Okay, if this was positive 150, it'd be 5 radical 6. The fact that it's negative, that we have this negative 1 on the end here, just introduces an I. You put the I before the radical, not after. Okay, now that we've discussed how to find I, or what it means, what it comes from, we're going to talk about the powers of I. Now, the definition of I, the definition is that I equals the square root of negative 1, something that's impossible to do in real life. You cannot square root negative 1, so I is an imaginary thing. Now, if you were to square both sides of this equation, just square this side and square this side, this becomes I squared, and this becomes the square root of negative 1 squared. Well, what happens when you square the square root? They cancel out, and you get I squared equals negative 1. Now, this is really, really useful. I squared is negative 1 means that even though I itself is something impossible, something imaginary, you cannot square root a negative number, so this is impossible. Okay, that's what makes it imaginary. I squared is a negative 1. Not a square root of negative 1, which is impossible, but a regular negative 1, which is a real number. So this is an actual real result, which means that it is possible, if you square your I, to go from being an imaginary impossible thing to a real thing, and that's what makes imaginary numbers useful. Okay, so what are the other powers of I? So we know that I itself is just I to the first power is I. We know that I squared is negative 1. Well, what's I to the third power? Well, I to the third power is simply I to the second power times I to the first power. You add the powers. So I to the third is I squared times I to the first. And we know that I squared is -1. And we know that I to the first is just plain old I. So what we get here is -1 times I, which is -I. What about I to the fourth power? I to the fourth power is the same as saying I squared times I squared, right? You would add the powers. And that would be -1 times -1, which is +1. So this creates a pattern here. We have I, -1, negative I, and +1. What about I to the fifth power? And I to the sixth, and I to the seventh, and I to the eighth? Well, watch what happens. I to the fifth power, isn't that just I to the fourth times I to the first? So it's 1 times I, which is I. I to the sixth, wouldn't that be 4 times 2? So it'd be I to the fourth, which is 1, times I squared, which is -1. 1 times -1 is -1. How about I to the seventh? It'd be I to the fourth times I to the third. You get negative I times 1, which is -I. And finally, I to the eighth, wouldn't that just be I to the fourth times I to the fourth? Because you would add the powers. So that'd be 1 times 1, which is 1. And you see the pattern repeats. I, -1, I, +1. And that keeps going forever, by the way. Like if I do 9, 10, 11, and 12, this is going to be the same as this. It's going to be I, -1, I, and 1. So the things you want to take away from this are that I itself is imaginary, but I squared is -1. So whenever you see an I squared, don't leave it as I squared. You must change it to a -1. And for higher powers of I, you can just realize that the pattern repeats. So anytime you have a power that's a multiple of 4, you're going to get a 1. Like for instance, I to the 100th power, 100 is a multiple of 4, 25 times 4, so that's just going to be a 1. And let's say you had I to the, 101st power. Well, the 100 part of it is going to be a 1, like we said here, but then you have that I to the 1, which is just this. Anyway, just a little information on how to deal with higher powers of I. You always want to simplify your powers. I'll talk about this more as we go along. Okay, now we're going to bring it all back to the first question. If you remember at the beginning of the lesson, we looked at this graph here on Desmos and that it did not have any real x-intercepts. We want to find the imaginary x-intercepts. Now, imaginary numbers are anything with the word I in it. The letter I in it. So 5i, for instance, would be an imaginary number because 5 imaginary things is still imaginary, right? 5 flying polka dot elephants is imaginary, even though it's 5 of them. So yeah, this is a real number. This is the imaginary unit, but 5 times something imaginary is still imaginary. However, you can also add real numbers to imaginary numbers. So you might have something like 3 plus 5i. Now this is a real number here, and this is an imaginary number. And when you put those two things together, you get what's called a complex number. Okay, and complex numbers are supposed to be written in the form a plus bi, where a is the real number and bi is the imaginary number. So when you combine real and imaginary, they're not like terms. Think of it like x. Like you treat I like x. You wouldn't add 3 plus 5x. You wouldn't like add those together to get 8x. No. So 3 plus 5i, same thing. You don't add them together. They stay separate. This is your a. This is your bi. A plus bi. So we're going to get an answer. We're going to get two answers, two complex roots. Like we saw on Desmos, there's going to be two imaginary roots, and they're going to be in the form of a plus bi or a minus bi. How do you find? Well, first off, what we're supposed to do, let's say we didn't know ahead of time what was going to be the answer here. What you're supposed to do to find x-intercepts is make the y 0. So if y is 0, you're actually solving the equation x squared minus 4x plus 5 equals 0. You might think, hey, this looks like reverse FOIL, but then you realize there's no two numbers that multiply to give you 5 that add to give you -4, so you realize you cannot do it that way. So you check the discriminant. You check the b squared minus 4ac to see if this is going to be something that can be solved or if it's going to be something that has an imaginary answer. So b squared minus 4ac, b is -4, b squared minus 4 times a, which is 1, and c, which is 5. You get 16 minus, and that's going to be 4 times 1 times 5 is 20. So you get -4. And -4, like we saw before, means that you're going to get two imaginary or complex, I'm going to call them complex from now on because that's the proper term, two complex roots. Okay, no real roots. Prior to this, we would stop and say no real roots and we wouldn't bother using the quadratic formula. But now we're going to use the quadratic formula. We're going to actually find out what those two complex roots are. So we're going to use the quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac, which we already know is -4, so we'll just put that in there, over 2a. Now b we said was -4, a we said was 1, and what we get here is -4, which is +4, plus or minus the square root of -4 over 2 times 1, which is 2. Now normally we would say, oh, square root of a negative. You can't do the square root of a negative, so we're stuck. But we've learned how to deal with that now. So let's come over here. Let's do a little more room here. What is the square root of -4? Well, you cannot square root a negative number. But what you can do is break it down, factor it, into a positive number times -1. So take the negative part and factor it out. You're allowed to do this, okay? So what is this going to become? Well, this square root of 4 is 2, and this has a special name. We call it, you got it, I. So what we have here gets replaced with 2i. The square root of 4 is 2i. This becomes x equals 4 plus or minus 2i over 2. So I substituted, I simplified, it's time to split. All right, meaning you're going to get two answers now. X equals 4 plus 2i over 2, and x equals 4 minus 2i over 2, like we do with the quadratic formula. You have the plus and the minus. You do one with the plus and one with the minus. You have two answers now. Now this can be reduced. This becomes 4 over 2, which is 2, and this becomes 2i over 2. Now just treat it like an x. If you had 2x over 2, the 2's would just cancel out. You just have x. Well, this is 2i over 2, so it's just i. And there's one of your answers, 2 plus I. And the one over here is the same thing. It's 4 divided by 2, which is 2, and -2 over 2 are going to become a 1, so minus I. Now, I didn't write the 1, but technically there's a 1 here. A plus BI, that's your B right there. A plus and minus BI. So you have 2 plus 1i and 2 minus 1i. If I go back to Desmos, because the center, the axis of symmetry is at 2 here, your roots are 2 plus 1i and 2 minus 1i, and that's how that all comes together. So when we come back here, hopefully this makes a little more visual sense now. Okay, so we have managed to solve a quadratic equation that actually has a negative discriminant, which is imaginary. No real answers, but doesn't matter anymore because now we can use imaginary numbers and find imaginary roots. Okay, we are done for today. I'll see you at the next video.
Check this.